Good day, everyone. It is nice over here for you and I because learning never ends and education is the key to an impactful life. My name is Anthony Nathaniel. Good day, everyone. Last episode we talked about the particulate nature of matter, but in this particular episode we'll be dealing with the elastic properties of solids. Now, elastic properties of solids are existent because solids are very closely packed together and they are held in relatively fixed position by strong intermolecular forces. So that is why we often study their elastic properties, and stick right to the end of this video to find out a lot about this part of physics. So what exactly is elasticity, by the way? Elasticity is the ability of a substance to regain its original shape and size after being distorted by an external force. Now what this means is that object basically has the ability that anytime you apply a force on it and that force causes a corresponding displacement, that object is actually capable of reversing the direction of that displacement and going back to its original shape, and that is the definition of elasticity. Then an elastic material is one that regains its original shape and size after the distorting force has been removed. So this is a diagram showing us the extension in the above one and the compression in the below of a spring, which is directly proportional to the applied force. Now in the above, when we added a double mass in the second instance, in the first instance it was a single mass, in the second instance it was a double mass for the extension. So you can see that the total length increased. Then when it was a triple mass, the total length now increased. And if you draw a straight line through the center of these masses, you will see it will be actually a straight line. It won't be curved. Now also in the case of compression, that's still the same case. So that proves that Hooke's law is obeyed, and I'll tell you about Hooke's law soon. So now with the aid of this graph, let's try to understand Hooke's law better. Now when we plot a graph of extension against load, you will see that the graph slopes upwards and then it curves towards the left. Now that slope where it curves upwards is from that zero, from O to P, is called the proportionality limit. So this is where the Hooke's law is obeyed. So basically Hooke's law says that the extension is proportional to the load applied within the elastic limit, right? Now beyond the elastic limit, the material loses its elasticity, and the difference between the proportionality limit and the elastic limit is that Hooke's law holds up to the proportionality limit, but the elasticity holds up to the elastic limit. So the difference is that basically Hooke's law equation can be used to calculate between 0, O and P in the graph, but from P upwards to other points of the graph, you cannot use that equation. So that does not obey Hooke's law. So this is just in case you get anyone asking you that question. So that's a suitable answer. Then next we have point Y is a yield point. That's the point between the elastic limit in which the elastic material has yielded all its elasticity. So between the elastic limit and yield point, the material still has some degree of elasticity, but once it gets to the yield point, it cannot return back to its original position, so it has become plastic. Now these are the basic points, and then we have the point B, which is the breaking point. That is when the material snaps and basically breaks or is distorted. Now let's stop it right there and let's go to the mathematics. Now basically, for those of you who have been waiting for the equation to drop, now this is the equation which says that force is proportional to extension, or rather in full notation, force is equals to Ke, where K is the constant called the constant of proportionality, which is also known as the elastic constant or force constant or stiffness of the material. So now let's solve an equation, an example to help us understand the Hooke's law better. Now in this example, we have that a force of 2 newtons stretches an elastic material by 30 millimeter. What additional force will stretch the material by 35 millimeter? Assume that the elastic limit is not exceeded. Now here we have our equation of Hooke's law, which is force equals to the elastic constant or the force constant multiplied by the extension. Then we also have the force here is given by 2 2 Newton. That's 2 Newton equals K plus K times 30 over 1000. So we are converting to meters. Now we calculated our constant to be 2000 over 30 Newton per meter. Then let the force stretching the material 35 millimeter be F. So we are looking for F now. So F equals KE. So we are going to multiply our new value of K, which is 2000 over 30, times the new extension, which is 35 over 1000. When you multiply that, you will get 2.33 newtons. So that means the additional force is the difference between the final and the initial forces. That would be 0.33 newtons. So this is how to answer questions like this. Now we have another concept which I want to introduce, and this is the Young's modulus. Young's modulus is equals to the stress divided by the strain, and we'll be talking about this in a subsequent video. We'll be doing some more analysis, but on the surface idea, Young's modulus is equals to the stress, which is the ratio of the force to the area, then divided by the strain, which is the ratio of extension to the length. So basically that's when represented by their symbols. Young's modulus equals F over A, then divided by E over L. So that is the statement of Young's modulus, and it is often applied in material science to understand the distortions and behavior of various materials under stress, strains, compressions, and other forces. Now let us round off this episode with the final equation that ties everything together. Now you should have, when you've watching this course, if you've watched the previous episode, you would have understood that I said work always has a corresponding force, which always has a corresponding acceleration. Now, and force also often has a corresponding displacement, but not always. But force, which has a displacement, is called work. But when it doesn't have a displacement, it is mere effort, which doesn't produce any useful work. So basically, now this work is basically the product of the force and the displacement, but not just the force, but the average force, because you know that the material actually performs two displacement, an extension and a compression. So when you extend it, it actually goes back to its original state. But before you have actually energized it to extend it. But when you release it, you're actually letting go of the energy you have given it, but you are depositing the energy in the body, and that energy you've given it is used again to return into its original state. So that shows that there's work done since it involves energy, and so the work is equal to the product of the average force and the extension. If we tweak the equation, we will to get the work as half Ke squared. So it's still the same thing, but when you substitute your for F equals to Ke in the first equation, you get your second statement, and this is how to get the work done in a spring.